All right. Hello, everyone. Welcome back to Math 162. Well, the few of you in here on time this morning, it feels like that's fewer and fewer each day, but that's okay. Like I said, we have the YouTube replays. I hope everybody is catching those if they're not here live. So we've got some important stuff going on today or tomorrow, depending on how you're doing it. Maybe some people are doing that particular thing right now, in fact. So in terms of homework that's due coming up, 6.5, due on the 8th, which is obviously today. And then we spent a ton of time last class working on 7.1, but didn't quite finish it. So I did not make that due date immediate. We will finish it today, as well as getting into 7.2. In fact, we're going to finish 7.2. So I thought I had that up here. And I will double check to make sure that that's right in my math lab. I'm pretty sure I have it already set up in my math lab correctly. I just forgot to write it on this whiteboard. So 7.1 we will finish. We won't have to spend too much time finishing 7.1. And then in the last hour and 15 minutes after that, we'll finish 7.2. I am going to have to kind of break up the videos a little bit today. I'll talk about that in a minute. I don't want to get ahead of myself. So test 2 today or tomorrow, whichever day you are available to take it. Remember that 11:59 p.m. tomorrow, Friday night, the 9th, is the absolute final due date for this test. If you email me a day or two later and say you forgot to take it, that's not an excuse. You won't be able to take test 2 at all. If you have some kind of medical documentation or anything like that, if that was a reason that you missed the test, that can be acceptable, and then we can discuss action items from there. But hopefully everyone will be able to take it on time like test 1. Y'all did a good job with that. So hopefully test 2 will be the same. Remember, there is no 6.4 for this test. We did not cover that material. And I'm realizing I still need to put that document in Canvas. I will make sure I get that done sooner than later. Again, it won't be tested on it all in here. It's just maybe you want to see those formulas. And if you want to see the formulas before I put the document in there, then just open your textbook to section 6.4 and you'll see all the formulas that you would have seen. So there is a formula sheet in Canvas for you. It's the same one we've referenced many times. Make sure you download that, print it, or have it available to you. Don't add anything to that. Remember, this is a no calculator test, no notes, no books, just the formula sheet and your brain and blank paper. Remember to show your work, show all your work, number your work. Make sure your name is on your work, upload it to Canvas within 15 minutes. I believe I already have, yes, I already have that, that spot active. It should be immediately under where you submitted it for test 1. Make sure you submit the right documents. I have no way of removing any submissions and then giving you a second attempt without giving everyone a second attempt for the Canvas submission. And I'm just not going to do that. So make sure you get it right on the first try. My pre-calc 2 students are generally pretty good about that. So hopefully y'all are continuing to be awesome. 2 hours for this test. If you have any accommodations that you need, email me and remind me, and we'll make sure that you get those. The review is still available in my math lab. Remember, that's not a graded assignment. Highly suggested that you do it though, so that way you understand what's on the test. Email me if you have any questions. Email me if you feel you deserve any partial credit. Remember to reference which problems, and then I'll get back to you in 24 to 48 business hours and let you know how that went. Should you not receive word from me in that time frame, shoot me another email and say, hey, Mr. Beckner, what's the status? Because sometimes things get lost and I'll have 3 classes taking tests all at once. So I'm sure I'm going to have a lot of emails over the next 2 or 3 days because of that. So again, if I miss it, just please be patient with me. I apologize. And I will get back to you as soon as you bump that email. So what did I want to say before I talk about the topics? Where we pick up with 7.1, we're going to start with example D, but I also want to remind you of the hows and the whys and the how do you determine if there's 2 triangles, what do you do when there is 2 triangles, how do you process it. So I'm actually going to replay about 3.5, 4 minutes of an earlier segment of the video you saw last time, again, just to make sure that we have that fresh in our brain. It's been a couple days. We're probably mainly focused on the stuff from chapter 6 because of the test. So I want y'all to see that again, and then I'll skip to problem D. So you'll probably hear me say, hey, we're about to do C. That's a lie. We already did C. Again, it's just a short replay of a clip. Then we'll dive into D. Then we'll do some area formulas, which I will talk about how I feel like they're in the wrong section, but that's not a big deal. It's a simple formula, in fact. And then after that, we will get into 7.2, the law of cosines. We will knock all of that out today. Again, I'll have to kind of skip a little section or two. I was having some technical problems when I was recording and ended up splitting the video into a couple parts. Either way, you'll get all the information. It won't matter. Per usual, I'll be in the chat if you have any questions, but let's go ahead and do that quick little review and then D.
So let's pick up where we left off in 7.1, the law of sines. So as a reminder about that formula, we've done several problems and not even close to being done yet. Here's our law of sines. Just the length of a side over the sine of its angle opposite of that side is equal to any of the other pairs of length of sides to sines of the angles opposite to them, whether you're using the Greeks the Greek letters or the just capitalized letters, and we've done both to make sure that we're used to them. We've talked about how you have some simple cases, like if you have two angles given to you, you know there will be one triangle and only one triangle, and you know you can start it off very easily by finding the third angle by just doing 180 minus the other two. Several examples. Then we got to what we call the ambiguous case, where you are given two sides and an angle instead, and it happens to be that the angle you're given is not between those two sides, and that's important. That is very important, because if the angle is between the two sides, then you would do the law of cosines, which would be in the next section. So you could have this angle or you could have this angle, but you can't have the one between those two sides, the one that connects the sides. So this angle right here would be the only option that you couldn't use for this. And we talked about how, given these parameters, it's actually possible that somebody just gives you some numbers and the triangle doesn't even exist. It's possible that someone gives you a triangle and there is just the one scenario, but it's also possible that just the heavens and stars align perfectly, that you could swing that length of A in or out and make either a smaller or larger triangle. And there can be two scenarios. Now, we haven't seen that case happen yet, hint, wink, nudge, but we have seen the one triangle and no triangle case. How do we determine whether there's two triangles? Well, once you have your second angle, so they give you one, you find the second, that'll be the first thing you do. You take the supplement of it, because it turns out that if there is a second triangle, the supplement of the first version is the second version. And I kind of rationalized it to y'all a little bit. And then we said, okay, if this angle, in addition to the original angle provided, if those are small enough to form a triangle, in other words, if they're less than 180 degrees, then that means the second triangle does in fact exist. So you complete your first triangle, then you use that supplemented angle to complete the second triangle. We said there's no triangle if your calculator spits out an error in the process, essentially. But it's nice to understand the rationalization of it. And we say that the rationalization of it is when you go to take an inverse sine, you end up taking an inverse sine of something larger than 1 or smaller than -1. Generally larger than 1, since we're dealing from 0 to 180 degrees, and sines are all positive from 0 to 180. So if this number inside, if you just calculated this number, whoa, that's really weird if you try and use the drawing tablet with paper on it. If this number was bigger than 1, which turned out to be 1.5, then it can't happen because it's undefined. And that's what happened for case B. So a reminder for problem A, which I should have said problem B just a second ago. When we found our second angle, we did its supplement, and it turned out that that angle along with the given angle was too big to form another triangle, which is why there was only one triangle. This one, again, the inverse sine didn't exist because the inside value was bigger than 1. And I think you know where we're going with C. Is this going to be enough space? I think it'll be enough space. Whoa, that was weird. So little a equals 7.
Sorry, I didn't mean to jump that far ahead for a second. I was typing in the chat and got distracted when I was about to skip that section. So here we are after we did that quick little review of the topics, how to tell, and then what to do when in this two triangle or even no triangle case. Now we're going to get on to D. This is picking up where we left off last time. All right. Thank you for your patience.
Little b equals 28. And I don't have to give you A and B. I can give you B and C or A and C. It doesn't matter. And then we'll go with angle, and I'm going to go back to Greek, alpha equals 12 degrees, or capital A if you prefer. But again, in my math lab or future classes, you could see it either way. When you get on a calculus, it's pretty rare that people use capital letters instead of the Greek letters. And if you go past calculus, you end up learning the whole Greek alphabet. And there's some really wacky looking letters in the Greek alphabet. Like one of them just literally looks like a squiggle. But we're not using that one. All right, so what case are we in? Well, we only have one angle, so we're not under the easiest case. If this angle was between these two sides, we would be under a case I haven't even taught you how to figure out yet, so hopefully that's not it. Well, that would be angle C or gamma if it was the one between these two. If I gave you legs A and C, angle B would be between the two. If I gave you sides B and C, angle A would be between the two. So this is the ambiguous case, which means it's possible it's one triangle. It's possible there are no triangles. It's possible there are two triangles. Don't worry, 3, 4, 5 triangles, not possible, never possible. So this is the ambiguous case, and I've already basically told you what this one's going to be, but let's establish it. All right, so I can't just go and find another angle really quickly by doing 180 minus two others because I only have one of it. So I'm going to have to do law of sines. And there's only one possible law of sines to do currently. It's taking the completed A's, the 7 over the sine. How much? Before I progress, I need to do this. Come on, go down. There we go. Perfect. Just give me some more space so I don't screw things up. All right, so doing the law of sines, we do A over sine A, so 7 over sine of 12 degrees equals the B over the B, sine B, so 28 over sine of, not B as I'm using Greek, sine of beta. Cross multiply, and you'll get 7 sine of beta equals 28 sine of 12 degrees. Degrees is a little low, isn't it? Then you're going to divide both sides by the 7 so that you can get rid of that and isolate the sine term. So what we get here is, wrong color, sine of beta equals 28 sine of 12 degrees over 7. Again, yes, they can reduce. I'm doing that intentionally, and you don't have to reduce. And then you take the inverse sine of both sides. So we go inverse sine of the left, inverse sine of the right, sine of beta, and then 28 sine 12 degrees over 7. Now again, we're kind of making a big assumption here that the angle is going to actually be between 0 and 90. But it's usually okay. It stops being okay in the next section, but we'll have a way to get around that in the next section. For now, we don't have a way around it. So the inverse sine and the sine cancel. So what we end up getting is that angle beta is 28. I'm sorry, I forgot my inverse sine. Definitely don't want to forget that. Inverse sine of 28 sine of 12 degrees all over 7. And again, that could just be 4 times sine of 12 degrees. We'll round that to the nearest tenth. Let me do this, just so I can still see the calculator on the screen. That's been a little annoying. Inverse sine, 28 sine 12 degrees, close it, divided by 7, close it. And we get 56.26 blah, blah, blah. Rounded to the nearest tenth is 56.3. is there a triangle 2 question mark? Is this a B1 or is it just B, or beta, excuse me? Is this beta 1 or is it just beta? If there is a second triangle, then the supplement of this would be the second version of the angle. So B2, beta 2, if it exists, would be 180 degrees minus 56.3 degrees. So that's 23.7, 123.7? Yeah, I had to check myself for a second. So again, that's if it exists. But does it fit? Does it fit? So this is where we take the angle they gave us, add this new second version, and if that value is small enough, if it's less than 180, then we know we're good. So we take alpha plus beta 2, and that would be 12 degrees plus 123.7 degrees, which would be 135.7 degrees, right? Right. And 135.7 degrees is less than 180. So yes, there is a second triangle. So now we call angle B beta 1, angle beta 1, which is 56.3 degrees. And then beta 2 would be the 123.7. Now again, anything prescribed does not have a second value. There is no little a2, there is no alpha 2, there is no little b2. We can only have second versions of things not given to us. These are fixed because we were told they are what they are. So for triangle 1, well, first of all, we already know, and I'm writing it for a third time, the first beta 1, is the 56.3 degrees. We got that pretty quickly. So we have A's completed, we have the B's completed, now we need to attack the C's. Well, the angle is the easiest to attack, not C2, gamma 2. I just said C, so it threw me off. Gamma 2, which is capital C2, that's 180 degrees minus alpha, which is 12, minus B1, which is the 56.3. See, I'm ignoring the B2 for a while. I'm pretending this doesn't exist until we get to triangle 2. But I don't actually want to erase it. So that's 170, 168. And that'd be 0.7, 111.7 degrees. That's our gamma 2 or capital C2, whatever you prefer. So we got our B1, beta 1. We got our capital C2 or gamma 2. Now all we need is that third side, which is little c2. We'll have to do law of sines for that. So we'll use the completed A's again. That's the nice thing. When you keep doing these over and over and over, you end up referring back to that same half of an equation. 7 over the sine of 12 degrees equals, now we're trying to attack the C's. So little c2 over the sine of its angle. Why did I write 1? Why am I writing 2's? Race, gamma, probably because I had just said B2 up there. That's my bad. Gamma 1, we're talking about triangle 1, gamma 1, 117, 111.17. 111.7 degrees, good Lord. 1 plus 1 is 17. I'm joking. You could cross multiply and then divide by the sine of 12 degrees, or if you want to get this in one step, multiply both sides by sine of 111.7 degrees, which would tell us that little c1 is equal to 7 times the sine of 111.7 degrees over sine of 12 degrees. Rounding to the nearest tenth. 7 sine 111.7 divided by sine of 12. And we get 31.2 blah, 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 so 31.3. And that's a length, so no degrees, 31.3. So that is what we're going to call little c1. 1, 2, 3, boom, triangle 1 is done. Everything is labeled correctly now. I fixed my 2's. Again, I apologize for that. Make sure that if you do any little mistakes like that, that you're able to catch them. That's what a good, I don't want to say mathematician, just a well-numerate student or person does, is they can catch errors on the fly. They're always checking themselves. They're always looking back at things and making sure everything fits and makes sense. All right, now we're up to triangle 2. So remember, we're still using everything given. We still have these 3 values. They haven't changed. But angle beta 2, side C2, and angle gamma 2 all need to be found. Well, actually, we already found one of them. We already found beta 2, because a second triangle existing all hinges on beta 2 being small enough, finding beta 2 and it being small enough. So, borrowed information, because we already found it, beta 2 was the 123.7 degrees. Box it up, ship it out, which makes gamma 2 180 minus the original alpha, which stayed the same of 12 degrees, minus this new beta of 123.7 degrees. And what do we get for that? What do we get for that? Is it 23.5? Wait, why did I say 23.5? Because I was looking at that. That's wrong. 168, 44.3. 44.3 degrees. So that's our gamma 2. We got beta 2, we got gamma 2. Now all we need is little c2, which we do law of sines to find. 7 over sine of 12 degrees equals c2 over the sine of gamma 2, 44.3 degrees. Cross multiply and then divide by sine of 12, or just multiply both sides by the sine 44.3 degrees, so that we get little c2 is equal to 7 sine 44.3 degrees all over the sine of 12 degrees. Remember, if you're doing this right, you'll notice a lot of similarities in structure. Look at C1 versus C2. The only thing that's changed is the sign in the top. So we approximate this to the nearest tenth. 7 sine 44.3. Close it, divided by sine 12. And closing those parentheses is critical. I think I did something wrong. I had a sign up there instead of 7. 7 sine 44.3. See, I got an answer that just didn't make sense. I looked at my calculator and I saw I made a typo. 7 sine of 44.3, close, divided by sine of 12, close, boom. 23.5 makes much more sense. And you'll notice I said that number earlier. It's because I was looking at my notes and I was like, wait, that doesn't add correctly. But then I realized, obviously, I wasn't looking at the correct number, was I? All right, 23.5. Because when I did it in my head, I had 44.3, saw the 23.5 and went, and then went, nope, that's because that was C2. That's our C2. Boom, boom, boom. 3 answers for a triangle means it's done. You want to put it all together, beta 2, 123.7 degrees. And I have a degree symbol here, which is not right. For C2, that was a length, not a degree. Gamma 2, 44.3 degrees. Little C2, 23.5. Not degrees. Which I never actually put all that information together for the first triangle. So for triangle 1, if you wanted to write it all together, B1 is 56.3 degrees, gamma 1, 111.7 degrees, little c1, 31.3. Not degrees, not degrees. There we are. When you pull back, you can see it's a pretty decently lengthy problem. It's a lot to keep track of. But we weren't doing any new math here. Literally nothing we did in this process was new. We're just putting a whole bunch of different processes together. These are very easy problems to just go and say, oh, it's only one triangle. If I don't see a student try to find a second triangle, in the past, I have gone back and awarded 0 credit for a problem if I felt it necessary, if they didn't even try. I'm not saying that's what I'll always do, but if I go back and look at your work, I see, oh, here's their 2 triangle problem, and they got half of the answers right because they got the first triangle, but they didn't even try a second triangle. While my math lab may give you 50% of the points of that problem, I may go back and say, well, honestly, you only deserve 25% because you didn't understand the bigger picture of things. So I do reserve that right, as I've pointed out before. Do I always execute that right? It depends. On a more traditional test, I actually make these problems worth more points, and I don't even tell which students or which problem it is. I'll say, okay, if a problem has 2 triangles, it's worth 9 points instead of just 6. But that's an if. I don't tell you, oh, question 7 has 2 triangles, question 3 has 2 triangles. No, it's just, if there is one, it's going to be worth 9 instead of 6 or 5 or whatever points. But I'm not giving a traditional test, not as traditional at least, so I'm just trying to run things a little differently because of that. So please, in your notes, make sure you're trying to see if there's a second triangle, but only try on problems where it's relevant, where it's this ambiguous case. If you try and make a second triangle out of a problem that gave you 2 angles, I can go back and take off points for misunderstanding information there. Again, I don't usually try and just hunt down points to take away from you, but I definitely have that right reserved. All right. So that's all the problems I'm going to do for this topic, but we do have one more type of problem to do in here, and I'm not exactly sure why this problem is in this section. I mean, I do know why, but I think it would make more sense to put it in the next section for reasons I'll explain. But the only reason it is in this section is because it has a sine instead of a cosine in the formula. All right, so let's pull back in. Make sure we got space. Oh, I do have plenty of space. The area, area of an oblique triangle. So remember, oblique means not necessarily a right angle in there somewhere. You better know the area of a traditional triangle. So the area of a right triangle, first of all, so this is different. It's 1/2 the base times the height. Where if you draw it from this perspective, this would be your base and this would be your height. Why is it 1/2 base times height? Because if you drew this, that doesn't look like an H, does it? I can do better than that. H. Because if you drew this triangle on top of itself, if you flip it across the hypotenuse, this would also be H, this would also be B. Now you have a square of width B and length H, or height H, however you want to call it, and that area is base times height, B times H. But there's 2 of those triangles, so you just half it because you really only had 1 to begin with. That's the entire reasoning behind the formula of a right triangle being 1/2 times base times height. Well, now we're talking about a triangle that is no longer right, it's oblique. So your triangle might look more something like this maybe. And we could show, and it's not very difficult to show, that if this is your height, you can project another triangle there, by doing some very simple trigonometry, and that height right there, well, if you call this h, and then you call this your angle theta, well, the sine of theta would be h over this value. And then you can just solve for h and say that h is that value times the sine of theta. And that's all the formula really gets. It's just one of these two things. I didn't mean to draw it there. You can, but it's actually better to do it here so that it's consistent. Let me draw the height there. This is just an arbitrary further distance out. So that h, if this is your theta, we would say the sine of theta is equal to h over, let me just call this distance c. So c, if you solve for it, it would just be sine of theta over, I'm sorry, it would be h over sine of theta. And then you can just plug in that into this, and what you end up getting instead is a equals 1/2 b times c times the sine of angle A. But that's only one possible reference out of all of those. It could also be 1/2 a times c times the sine of angle B, or it could be 1/2 a times b times the sine of angle C. So you've got three versions of the area formula just based on which two legs and which angle you have. Now, this is not the case that we were just talking about with the ambiguous case. This is the angle between these two given lengths. So what we're saying is if we have a triangle drawn up like this, if this is leg A and B, then this is angle A. Or if you have your triangle drawn up like this, if we have A and C, then this is angle B. Or if we have a triangle drawn up like this, we got C and B, and then this would be angle A. These two cases are swapped, but that's all right. See, this picture actually goes with this case. This picture actually goes with this case. I'm just showing all three of them, not necessarily paired up evenly. So this is how we can find an area of an oblique triangle, but the things you have to be given are very specific. You must be given what I call a corner of information. I call it a corner of information because it goes leg, angle, leg. That's a corner, or this is a corner, or this is a corner. So a corner of information means, more specifically, you have two sides and the angle between them. I will be using that phrase in the next section quite liberally. And this, again, is not the case of anything having to do with law of sines. This formula, in my opinion, should not be in the law of sines section. But I think the reason a lot of trig textbooks put it in the law of sines section is because the formula has sine in it. Okay, I get that. But in the next section, when we learn about the law of cosines, these three cases are what we're going to be dealing with. So I just feel like personally it would have made more sense to throw this formula in the law of cosine section, even though it has the word sine in it. Oh no. But again, it's the same scenario. This fits more of a law of cosine scenario better than a law of sine scenario. It's not a very tough formula to memorize. You might say, well, it's three of them. So yes, it is, Mr. Beckner. You know what I'm going to tell you. This is one thing to memorize, and you just have three variations of it. It's a 1/2 because formula of area of a triangle is 1/2 base times height. This is basically your base, and this is basically your height. just depending on how you orient the triangle. So it's 2 legs and then the different angle with a sine. 2 legs and then a different angle with a sine. 2 legs and then the different angle and a sine. That is an easy formula to remember. It's one formula in my opinion, not 3. I will never put that on a formula sheet for you. I will be honest, it is not something we're going to use over and over and over and over and over. It is something we'll see in this section. Maybe one more problem somewhere down the line, but that's pretty much it. I'm not saying it's not useful. It is extremely useful. It's just for our course, we can't really extend the concept much past that, so it's kind of a dead end for us. But again, it does have lots and lots and lots and lots of applications. Maybe you're going to go build a triangular garden and you want to know how much soil you need to build, or you need for the build. And you know the lengths of fence, the A and the B here, and then you can just get a protractor and measure angle A, and then boom, you can calculate the area. I know a lot of people don't build triangular gardens, but I do know at least one person in my life that has, and I taught them how to find its area. And they went, holy cow, math is good. Or something like that. I'm paraphrasing because it was years ago. All right, example, what are we up to? 3. Find the area. Okay, I'll actually draw a triangle for the first time in a while for a problem. If it looks like a right triangle, don't assume. This will be a 7, this will be an 8, and this angle right here will be 73 degrees. See, not a right triangle. Now, I don't care whether you call the 7 A or B or C. I don't care whether you call the 8 an A, B, or C. What I care about is that you understand you have a corner of information, which means you can use the formula. So the area is 1/2 the product of the legs, 7 times 8, times the sine of the angle between them. That's it. There's no crazy algebra. There's no second triangle, none of that goofy stuff. And then guess what? You just put in a calculator and round however they tell you to round, which me classically, I like 1 decimal. So 1/2 times 7 times 8. And yes, I could have done 0.5 times the sine of 73 degrees. And we get 26.77 blah, 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 blah. So that's 26.8. So that's our area. I did not give any units, so this is unitless. If I had said that this was 7 inches and 8 inches, this area would not be 26.8 inches. It would be inches squared. Don't forget that. Handwritten test, I would definitely dock someone for that. You have got to understand units in here. How area, volumes, how their units are squared or cubed. That's it. That's the whole problem. B, I'm going to go back to giving you the information just straight up. A equals 40 meters. Little c equals 121 meters. And let's go angle beta. Let's go back to the Greek. And that's 11 degrees. This angle is not the angle opposite of A or C, so this is a corner of information. I could draw it up and make it look exactly like the last one if I really wanted to. It wouldn't look too much to scale if I'm calling this 11 degrees. So maybe you just want to make it a little tighter like this. That almost looks right, but it's not. But I never asked you to draw it, so you don't have to. Corner of information, formula. Doesn't matter if this is A and C or A and B or B and C, as long as this is not one of those angles opposites. So it's 1/2 the product of the legs times the sine of 11 degrees. 1 divided by 2 times 40, which is 20, times 121, times the sine of 11. Drum roll. We get 461.757, represent. Sorry, I'm silly. 461.8 rounded to the nearest tenth. 461.8. And if a student bucks this up and shipped it out on a handwritten test, that's wrong. I'd give them tons of partial credit, but it's wrong. Now, oh, I forgot my units. That's right. Well, those are meters, so this is meters. Well, nope, that student would not get any more partial credit. Because we're talking an area, that's meters squared. And the reason is because this was 40 meters times 121 meters. If you actually wrote your units, if you did proper dimensional analysis, meters times meters is meters squared. So that's our area. This angle right here makes a major difference on the area. What if that angle had been much, much larger? Let's say it was 100 degrees instead. So let me just pull up that problem again, and let me just make the sine of the angle, instead of 11 degrees, I'm going to make it 100 degrees. So now instead of our triangle looking something like this, with a really tight 11 degrees, and again, this is not right, now it's a much wider degrees, which makes that the ending point. Maybe that'll cause the area to be larger, smaller. Let's see. Because a lot of people might think that angle doesn't really make much of a difference. But look at that. That is about 5 times the area, just from going from a really narrow angle in that corner to a really wide angle in that corner. Narrow angles tend to make narrow triangles narrow, less area. Once again, I feel this would have been more appropriate in the next section because this is the scenario of information we're going to be given when we use the law of cosines. Law of sines, we wouldn't necessarily have this 8, we might have, this might be the 8 instead. And then that angle is not between them. This would be the angle between them. So this would be a situation. All of the different sides, angles, maybe a second triangle, but with just these 3 numbers, I can't find the area. I would need to find this angle or this side. Now, I certainly can do that in the processes we've just done. I could certainly complete this triangle, then use any of the 3 corners of information, because you would have all 3, and find the area. And all 3 of those areas would match 100%. So our example 4, just FYI, is text. Homework. Problem number 51? Yes. So if you want the reference, if you got your textbook next to you, you can do that. I'm going to type this quick. The Leaning Tower of Pisa. Please excuse me not capitalizing things. In Italy, leans at an angle about 84.7 degrees. Figure shows that 171 feet, I'll get the typo fixed later, from base of the tower, the angle of elevation is 50 degrees. Find the distance nearest 10th of a foot from the base top of the tower. I don't have to give you an image for this, but I will. The information is all there. But the image that they're describing is we have our Leaning Tower of Pisa. So it kind of looks like a cylinder vertically. Let's have the tower be in red. But it's slanted a little. And I'm exaggerating a little bit here. But here's your tower. Then what we're doing is we're making a triangle out of this. So from the top to its base, this angle right here is 84.7 degrees. Then they say the angle of elevation to the top is 50 from a distance 171 out. So something like this. So we are 171 feet. That's from here to here. That's just the width of that triangle I just drew, from base to some point of observation. And someone observes that that right there is 50 degrees. So it's very well measured that this angle of elevation for the Leaning Tower Pisa is about 84.7 degrees. And someone could just walk out 171 feet. They can measure it exactly. Then they can get a protractor, a laser device, or something like that and measure 50 degrees to the top. Now, the question we have is, find the distance to the nearest tenth of a foot from the base of the top. In other words, we're trying to find what was supposed to be the height of the tower. So I'm going to put this in little parentheses. It's not an actual height because heights are always supposed to be just straight up vertical. But when the tower was designed, it was supposed to be the height. We're trying to find how tall the structure was. If you laid it on its back, side, whatever, from end to end, bottom to top. Now you might say, well, how can we do this? You gave me two angles and a side. Well, actually, that's pretty easy, right? The two angle and a side case is going back to the beginning. So this is the AAS case or ASA case, AAS in particular. Two angles and a side. So the easiest thing to do is find the third angle. So what angle is this? I don't know. Let me call it angle C. So angle C, capital C, would be 180 degrees minus the other two angles. So 50 degrees minus the 84.7 degrees. So that's 130. 50, 45.3. Yes, 45.3. So that's that angle at the top. Did I actually need to do that? Yes, actually I did. Maybe, maybe not. I don't know. I did it anyways, but in fact, I didn't actually need to. Maybe, maybe not. I'm sorry, I'm messing with y'all. All right, so we know all three of the angles and we have this side completed. Now we're trying to find the distance here, this height. So we need a completed pair of information. Well, in fact, we need it. The completed pair of information is the C's. So that's going to be the first side of our law of sines. So law of sines states we're going to go little c over sine of angle c, so 171 over sine of 45.3 degrees. And that should be equal to. Now, do I need this distance if I call this a b? Do we actually need it? Well, nowhere up here did they say we needed it. So while I can certainly find it, and I could use this angle and this b to find it, I don't have to, so I'm not going to. All we need to find is h. Well, here's the angle opposite of that, so that should be what's on the other side. So we'll go h over, and I could have labeled that with any other letter I like, the sine of 50 degrees. All right, well, to solve for the h, you can just simply multiply both sides by the sine of 50 degrees. You can cross multiply and double step it if you like. Nobody's going to care which method you take as long as you got a method that works. And that's going to tell us that the height of the Tower of Pisa, again, not the actual height, just the height of the building itself if it hadn't been tilted, will be 171 times the sine of 50 degrees over the sine 45.3 degrees, which they told us to round in the nearest tenth. No surprise. 171 sine of 50. Close it. Divided by sine of 45.3. Close it. And we get 184 point, when we round to the nearest tenth, 3. 184.3. 184.3. This was measured in feet. So there we go. The Leaning Tower of Pisa was supposed to stand 184.3 feet tall. Here's a fun problem to try out. And this is not, I'm not going to do it, but you could ask, how tall is it actually? So here's your triangle with your h, and you know that distance. Well, what you do is you make this the actual h. You end up making a right triangle. You've got this angle still, it's 84.7 degrees. You know this is 184.3. So you can use the hypotenuse. We can just ignore all of this. So we can go h, 184.3, and the angle of 84 0.7 degrees, and we could use sine. We could say the sine of 84.7 degrees is h over 184.3. I am going to do it. In fact, if you multiply both sides, you'll get what I'm about to put in the calculator. 184.3 times the sine of 84.7, and you get 183.5 feet. So it's only about a foot less in height than it was supposed to be. So that angle isn't actually too significant on its height. Now, if that angle is 50 degrees, if this thing was really cranked over, the height would be significantly shorter then. Now, again, the actual length of the building, which we called the height in quotes, is still 184.3. But again, if you actually just tried to measure straight up vertically, this distance right here, that is what would be this 183 and some change. And that wasn't actually part of the problem. It was just something I did for fun.
All right, last swap. Give me a second.
So last class, we finished up 7.1, which was the law of sines. It was a pretty lengthy section because of all the different cases. We had the nice easy case we did at first where we were given two angles. Then we had the ambiguous case where we had to determine whether it was no triangle, one triangle, or two triangles. A lot of little weird oddities in that and just things to keep track of. And now we're finally ready to do the final case of being able to solve a triangle as long as we have 3 bits of information. So as a reminder, the law of sines was when we had a triangle and you knew like this side, and this angle, something like that, where this angle was not between them. This was a law of sine scenario, and this was the ambiguous case in particular. Law of cosines is going to be where maybe we had the sides A and B still. Also, I wrote that as a C, and that is completely wrong. That is not angle C, that is angle A. Please forgive me for that. Law of sines, you'd be given this bits of information, or angle B, either angle A or angle B, but you could not be given angle C. The law of cosines is when we do know angle C, or angle gamma, whichever you prefer it. So this is where we have that, what I call a corner of information. That's when we use the law of cosines. Now, when we have a corner of information, we're going to have some things that could mess us up along the way. We're going to have to be very careful. You can punch things in a calculator and it'll give you answers, but if you weren't careful at one point throughout the problem, all those answers can actually be wrong. It has everything to do with how inverse sine and inverse cosine work and how they are bound. I've mentioned several times throughout this class that issue will keep kind of coming up here and there. So those are the 2 scenarios we're looking at. Law of cosines, explicitly this, a corner of information. Now, that is one of the scenarios, or you can also have the scenario where you know all 3 sides. You know this side, and this side. And you might be thinking, well, Mr. Beckner, you told me that the 3 angle situation isn't even solvable because it's infinitely many side lengths. And that was true, but that's not this scenario. If you know these side lengths, then these angles are a fixed value. There's not going to be infinitely many possible angles to solve that. So this is the side angle side, the SAS case. Don't give your teacher any sass. Ha ha ha. And this would be the side case whereas the law of sines was side-side angle. And we said we don't do it the backwards way for obvious reasons. So again, law of cosines. So law of cosines needed for the sine angle side case, again, the corner of info that I like to call it, and the side case. You can't start out those cases with law of sines. You will need the law of sines ultimately, but you can't start the problem with the law of sines. So I'm going to give you three formulas. Admittedly, all three of these formulas are the same, just with different letters, kind of like the area of an oblique triangle. I said there was three area formulas, even though they were all the same, just with different letters. Kind of like the law of sines had three sides, which are all the same, just with different letters. So our formulas. No proof, just giving them to you. This would be completely awful to prove. One of the worst things to prove for us. A squared equals b squared plus c squared. Oh, that's just Pythagorean. What are you talking about? No, that ain't it though. Minus 2bc times the sine, I'm sorry, cosine of angle A. So if you had the side lengths b and c and angle A, you could find the length of A based on this formula. Now it says a squared, so you'd have to square root it. If you think you need to plus or minus square root it, that's a great idea, but geometry, we generally don't need the minus because you can't have negative lengths. All right, the next formula is b squared equals, and then it's literally going to copy paste this, except instead of b's and c's, there'll be a's and c's. Instead of this being b and c, it'll be a and c, and instead of this being angle A, it'll be angle B. So we go a squared plus c squared minus 2ac times the cosine of angle B. Or the third version, c squared equals, I think you know or have an idea of what these might be. So that's c, so these are the a's and b's, and then minus same product, 2ab, and then a cosine of angle C, capital C. You must memorize at least one of these formulas or all three if you really feel the need. Me personally, I really like this one if I was just going to memorize one and then cookie cutter the rest to fit it. Some people really like this one because then you've got the C solved in terms of A's and B's. It's up to you. Some people say I memorized all three just on themselves. Whatever works for you, but that doesn't seem like a great idea to me. Because these are so similar, just remember it conceptually. One leg squared is the sum of the other legs squared. If you just had this just looks like Pythagorean, although it would have been c squared equals a squared plus b squared, but remember this isn't a right triangle, so don't try and relate it too much. So what you might even say is, okay, well you said Pythagorean and this one has c squared, so maybe that's why you like this version. So you have the Pythagorean part, but then there's an extra little detail. This basically just accounts for the fact that it's not a right triangle. This factor being subtracted is just a, how do I want to phrase it? It fixes it. It accounts for it. So this right here kind of looks like a factoring formula, minus 2ab, 2 times the product. It would be like a squared minus 2ab plus b squared, the pre-factored version that is, but then the cosine of the angle between them. This letter should match this letter. This letter matches this letter in terms of lower and upper cases, that is. So I don't care which one you memorize to get all three, or if you're memorizing all three, or whatever it is you're doing, but I will not give you that formula ever on a test. Final, anything. You got to know them. So again, that's for a corner of information, something that looks like an angle C and then side lengths A and B. So SAS, I'll finally write it down, is a corner of info. It's not literally a corner. I mean, I'm not saying it's just this is the corner. I'm saying imagine that you didn't draw, oops. Imagine that you didn't draw the other side of the triangle. That's your corner. But of course, the triangle is completed. All right, so before we try this out, I need to point out something extremely critical. So lots of asterisks for this one. Remember, the law of sines, excuse me, that the inverse sine is only valid from negative 90 degrees to positive 90 degrees. In other words, quadrants 1 and 4. This means that if you try to find an angle larger than 90 degrees, you can't by using inverse sine. You can't do it. Your calculator is going to tell you an answer that is wrong. It's not going to say it can't do it. It's just going to give you a wrong answer. Because it's going to get this information and think, oh, okay, well, if you've got these lengths of sides and these other angles and such, and that would mean it's going to be positive or negative, whatever. I'm just going to give you an answer of quadrant 1 or 4. If it's positive, I'll give you an answer in quadrant 1. If it's negative, I'll give you an answer in quadrant 4. But if your angle that you're supposed to be finding ends up being, say, 115 degrees, which would have been quadrant 2, inverse sine isn't valid there. So it's going to say, all right, well, it was positive, so I'm just going to give you the reference angle put in quadrant 1. Now, with that trick, you can, if you know all of this stuff is happening, you can then put that reference angle in quadrant 2 to find the real angle. But I'm gonna say that probably 99% of people don't ever consider that, admitting that even I have made that mistake. So I've already mentioned that with these law of cosines problems, when you're given a corner of information, you'll start out with the law of cosines, but then to find the other information, you're going to go back to law of sines because you'll now be able to, and it's a much easier formula to use. So this means if you try and find an angle larger than 90, you can't. But how are you going to know? Because you only have one angle initially. The second angle you'll find by law of sines. The third one you'll find by doing 180 minus it. So how can you tell whether an angle is going to be greater than 90 or not? You can't, but you can at least throw out the scenario that it might be greater than 90. So here is your hint, your approach, not necessarily a hint. So to avoid this possibility, when you do law of sines, find your second angle, make sure that you are not using the largest, let me say longest, side. In other words, do not find the angle opposite the largest side. So this is why that's going to work. The largest angle must be opposite the largest side. So if there is an angle bigger than 90 degrees in the triangle, there could only be one of them. So let's say that 115 degrees. There's no way you can have another angle that's bigger than 90 degrees because even if it was 91, 91 plus 115 is more than 180. So there's only one angle that can be bigger than 90 degrees, and that angle will always be opposite the largest side. So just don't use the largest side in the law of sines, and boom, you'll make sure that you don't have that issue when you put it in your calculator. I will again point this out. I have made this mistake. I've made this mistake in class teaching it before. I am literally looking at notes. I keep this from many years ago. I have one problem that I always keep to remind myself. I taught one wrong initially, and then I looked at it and I was like, uh-oh, we used the law of sines on the longest side. Didn't mean to do that. So I keep that as a relic, and I'm going to keep it for the next 20 years for the same reason. It's a nice thing about making mistakes. When you make mistakes, you'll learn not to make them again as long as you figure out that it was a mistake. All right. Now, this issue with inverse sine, this issue might also happen with inverse cosine later, maybe, maybe not, or maybe we're going to use inverse cosine on a specific parameter to make sure that this can't happen with the law of sines, but it's going to come up again. That's all I'm going to say, but not yet, not for a while. All right, so with all these details said, we got our formulas that we'll scroll back up to, at least for the first problem, maybe the second problem. We know that when we get to the point where we're doing law of sines, that we're not going to attack the largest side because that would find the largest angle, and that might be bigger than 90, and inverse sine wouldn't pick it up. Okay. So here's your process. Here's the order you should do things. In the SAS case, do a law cosines first, find the third side. I know what's going on. I want to, whoop, not that button. Do this, remove, boom, there we go. Do law of cosines to find the third side first. That was gonna bug me. Then do the law of sines, not with the largest sides angle, to find second angle, and then do 180 degrees minus the two angles to find the third angle. So I'm gonna go ahead and spoil something. There is no second triangle possible with these. It never is, never will be. There's always one triangle. It's never none, it's never two, it's always one. So this is our process for the side angle side. Do a law of cosines, then a law of sines. Make sure you're not finding the angle opposite the largest side. Now, if you already have the largest side and the largest angle, that's okay. If you already have an angle prescribed to you that's bigger than 90, the issue won't even be an issue. All right, so let's get it. Let's try one. Example 1. Complete triangle. I can give you these as an image, or I can give them to you as a list of just parameters. Let's go back to giving you an image. This will be A. So let's go triangle. Don't assume this is equilateral or right or anything like that. I'm going to call this side C. I'm going to call this angle 32 degrees. This side length will be 10, and this side length will be 12. I didn't have to call that side length C. I could have called it A. I could have called it B. I'm just choosing to call it C. I'm calling it C because that's how I'm going to use my formula. I'm going to go with the third version of the formula, which you can still see peeking at the top of the screen right here, because I find that a lot of people prefer that one. I may have actually said earlier, incidentally, or accidentally, that I like the first one. That's wrong. I do like the third one. I like this one because it looks like Pythagorean, then it kind of looks like a factoring formula. I like being able to relate things to other things I already know. It's less memorization. Patterns are wonderful. All right, so I get to call that C because I never was given any assumptions on letters. So that was my choice, which would make the rest of everything, I could call them angle A and B, or angle A and B in whatever order. I'll decide that later. So for now, C squared equals, I'll write the formula I'm going to use. A squared plus B squared minus 2AB cosine of angle C. So this would be C squared equals, I'm going to call the A the 12, so this will be 12 squared plus, then that makes the B the 10, 10 squared minus 2 times 12 times 10 times the cosine of 32 degrees. Now, if C squared is equal to that, we could go ahead and put this in a calculator, and it's going to give me a whole bunch of decimals. That's whatever. But I like to go ahead and show that C would then be the square root of everything. If C squared is this value, that means C is the square root of it, not plus or minus, because we're talking about a length of a side, there is no minus. So the square root of 12 squared plus 10 squared minus 2 times 12 times 10 times the cosine of 32 degrees. I'm going to put this in a calculator. That's why I'm not even writing that that's 144, and that's 100, and 24, 240 cosine of 32 degrees. I'm just going to jam that in the calculator as you see. That was my pre-calc class earlier, ignore that. So big old square root, 12 squared plus 10 squared minus 2 times 12 times 10 times the cosine of 32 degrees. We should probably make sure we are in a are in degrees. We are, that's good. Drum roll, ba-da-da-da-da-da-da. We get 6.36, and I'm going to do my usual round to the nearest tenth. So this is approximately 6.4. Let me pull that calculator up for another second. So you can keep seeing that. See, if I'd done all the 12 squared stuff first, let me just pull that up, delete the square roots. If I do this as 2 steps, so do all the math inside the square root, square root of 40.46, and then take the square root of the answer, you still get that. But notice if I take the square root, let's say I rounded that to 40.5 before I took the square root, which is a bad idea. Now this answer is still pretty close. It's still going to round to 6.4, but you can see that it is not exactly the same. So that truncation or round off error, taking an let me start that over. Taking a number that's been rounded and processing it and then rounding it again, you can see how that could have ended up staying at 6.3 after rounding, or maybe it bumps way up and it becomes 6.5. That's why I just don't like to take a rounded number and process it. That's why I did square root of answer, or type literally square root of 40.46, blah, 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 blah. It's not the end of the world. I will say 9 out of 10 times, maybe even more than 9 out of 10 times, that rounding that to a 10th before square root is going to be okay. But you're going to be mad when that 1 out of 10 times happens, aren't you? So just best to leave it alone. All right, so now we'll use the law of sines to find. So let me go back and label things. We said I called that C, so that was opposite angle C. We called the 12 little a, so that means this is angle capital A, and that would be angle capital B. So some people will think we can use the law of sines to find either of angle A or B, but that's not quite true. Sometimes it's true, sometimes it's not. And if you don't know which case you're in, you're going to get it wrong maybe, I don't want to say half the time, but you'll get it wrong sometimes. All right, so use the law of sines to find. All right, make sure you are not using the longest side. So the longest side up here was the 12, so do not find A. We don't want to find A with the law of sines because it's possible that that angle is bigger than 90. It's possible, it's not a guarantee. We don't know right now, we don't want to risk it. So we've got to find angle B, we have to. Otherwise we're flipping a coin and putting fate in our hands. So law of sines, that's A over sine A equals B over sine B equals C over sine C. The thing we have completed are the C's. Now you might say, well, Mr. Beckner, you said you don't like using rounded numbers. We don't really have an option at this point. If you wanted to, in that formula, put the big, beefy 6.36, blah, 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 you can, but let's just roll with the 6.4. So 6.4 over the sine, not cosine, of 32 degrees equals, now we got to go after the B's, which was the 10 over the sine of B. We're going to cross multiply, which will give us 6.4 sine of B equals 10 times the sine of 32 degrees. We're going to divide both sides by 6.4, which will give us that the sine of B is equal to 10 sine of 32 degrees over 6.4. And then we take the inverse sine of both sides. Like so. We do that because inverse sines and sines cancel, but only if we're in quadrant 1 or 4, which, as we said, A could be bigger than 90. So A could be in quadrant 2, so we wouldn't be able to guarantee that this aspect is true if we attacked A. But for B, because it's not opposite the largest side, angle B is definitely less than 90. So B will be the inverse sine of all that jazz, which when we round to the nearest tenth, let me do this. So, that's a little too much, isn't it? Here we go. So, inverse sine 10. What happened? 10. Then the sine of 32 and close it, divided by 6.4 and close it. And we end up with 55.8 9, blah, 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 blah. So rounded to the nearest tenth, that's going to be 55.9 degrees. So B is approximately 55.9 degrees. Now your homework might say round to the nearest whole, and admittedly, because we rounded because we rounded this to the nearest tenth, I have a strong feeling that this is probably off by a couple of tenths, maybe 2 or 3 even. It's probably like 56.1, 56.2 maybe. If I had used the exact number in there instead of 6.4, so that was, let me show you what I mean. If I bring this whole problem back, instead of doing 6.4, let's go 6.36148229, then close it. And I was right. We're off by about a half of a degree, in fact. That is the error propagation I keep talking about. So again, this is going to be good enough for us. I believe that my math lab for these types of problems tends to tell you to round in the nearest whole because of that, because both of these would have rounded to 56 degrees. But let's just go with what I have on the screen. Let's accept the very small error just for the sake of completion. All right, so that was angle B. So we've got length C. We've got angle B, which means the only thing we have left to find is angle A, which we just do the 180 minus the rest. So A would be 180 minus the 32 degrees minus the what I'm calling 55.9. I've already showed you that this is not exact. And if you really want to pull out the calculator, if your brain's hurting at this point, feel free. It's already staring me in the face, so I'm going to use it. And you get 92.1 degrees. That's a weird looking 9. So if we had used the actual answer, or a much better answer of 56.4, we would have done 180 minus 32 minus 56.4. So 91.6 is a much more exact answer, but I'm saying that 92.1 is perfectly fine for what we're doing here. And look at that, this is bigger than 90, which means if we had done the law of sines to find angle A, law of sines on A would fail. Don't believe me? Check it out. So in blue, I'll just show you that fact. So let me pull back so I can see everything. So if we tried to do the A's, we would have gone for the C's, that was the 6.4 over the sine of 32 degrees equals 12 over sine of A. After you cross multiply and solve, I'm not going to show all the work, you'll end up getting that the sine of A is equal to 12 sine of 32 degrees over the 6.4. So A would be the inverse sine of 12 sine of 32 degrees over 6.4. So let's type that out and see what happens. Inverse sine, 12 sine of 32, close, divided by 6.4. And we get 83.5 degrees, which is not the answer. It is wrong. It is wrong because the thing that is inside of it is a positive value. So the inverse sine function in your calculator is going to assume that we're supposed to be in quadrant 1, but in reality, the construct of this triangle, this is 91.6. I think that was yeah, 91.6, which we called 92.1. We accepted the half off. It's fine. But again, because your calculator thinks this is supposed to be in quadrant 1, it gives you an answer that's in quadrant 1. And it's wrong. And it's not like you can just take the reference angle of this, and put it in the other one. It would not give you the correct answer. I might have said that earlier. I said it might work, but in fact, it actually doesn't. Taking that as a reference angle and putting it in quadrant 2 would actually give you like 97 degrees roughly, 96.5, something like that. So that is why You have to be very, very careful. And again, if that angle wasn't bigger than 90, it would have been fine, but you don't know whether it's bigger than 90 or not. The only way you would know is if the angle we gave you, if this was bigger than 90. And guess what? I don't like giving you angles that are bigger than 90 because I want you to be on your toes. I want you to know these ins and outs of this weird scenario. Because these little issues can become major ones in the long term. Imagine you're working for a construction company and you actually have to do some of this math, which is absolutely possible. And then you build your frame incorrectly or whatever it is you're doing with this triangle. I know triangle frame, that's not exactly normal, but you get the point. I'm saying you could build something wrong, you take it to boss man, it's like, why'd you make this an 83-degree angle? It's supposed to be 92. Come on, get with it. And if it's the 5th time you've done it, maybe he fires you. So don't get fired. Nobody wants to get fired here. Gotta make that bread. But the process itself is normalized. Law of cosines, then law of sines, then 180 minus the rest. Just when you do that law of sines, you gotta be careful. All right, so let's do another one. And I'll give you the image for this one as well. So let's give you a triangle that looks like this. Again, if it looks equilateral, don't assume that. If I say that's 10 degrees, it's very obviously not an equilateral triangle. It'd have to be 60 for that to be the case. This is not drawn to scale. No mathematician draws us triangles to scale. And then this is a 31. So I've given you a corner of information, side, angle, side. We don't go side, side, angle because it's a lot easier to go this way. Someone might think, oh, side, side, angle, but we would want this side to be the next thing we have, not this one. We're skipping too much to call this side, side angle. All right, so that's law of cosines. No matter what you decide to call these things, it doesn't matter. I want to use a different version of the formula. So I'm going to use the one that says a squared equals b squared plus c squared minus 2bc cosine of angle A. So that means I'm calling the 24 and the 31 the b and the c, which means the 10 degrees has to be my angle A. So I am deciding to call this A. The 24 and the 31 I could call b or c in any order. I'm going to choose to call the 24 the b for no particular reason, and the 31 the little c. Again, my choice here was arbitrary. I didn't have to do these. I could have called the 24 little a, the 31 little b, and this capital C for the angle. The cool thing is when you plug those numbers into the formula, no matter which of the 3 formulas you use, no matter which of the 3 lettering choices you use, all the numbers will look exactly the same. All right, so our little a, so we'll have for our law of cosines, we get a squared equals 24 squared plus 31 squared minus 2 times the product of those, 24 and 31, and then times the cosine of our angle, which is 10 degrees. And you are more than welcome to square the 24 and the 31 and multiply all that other jazz out. But it's honestly not worth the effort because if this is a squared, you know you're just going to take the square root and you know that you're going to jam all those numbers in a calculator. So why bother simplifying along the way? If you simplify along the way, you're bound to make a mistake somewhere. So that's exactly what I would type into my calculator right there. Just keep it simple. All right, so let's do it. Big square root, 24 squared plus 31 squared, then minus 2 times 24 times 31 times the cosine. I don't actually have to hit times, but I like doing it anyways for the 10 degrees. And then we close up the parentheses for the cosine, close it for the square root. Admittedly, since it's at the end with this calculator, I don't have to, but again, it's just good notation. And we end up getting 8.46 blah, 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 blah. We're going to round to the nearest tenth. So that's about 8.5. Now, again, what you might want to try out on your own, just kind of studying this concept of error propagation, maybe do all of the math besides the square root, the 24 squared plus the 31 squared, blah, 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 hit enter, and then round that to the nearest tenth, then take the square root of it. I'm pretty sure that you're still going to get that 8.46, but then after that, it's going to be different numbers, and you'd still round correctly. And what's cool in calculus and beyond is you actually study the error propagation of functions themselves without putting any numbers in there. And you can talk about how square roots errors actually don't propagate too poorly. Whereas if you have like an x squared or an x cubed, they do propagate, and the bigger the exponent, the worse it propagates. And that's because cubes make numbers bigger, so it would make an error bigger. Square roots makes numbers smaller, so it would probably make an error smaller. That's a very basic concept of it, but actually doing the calculus of it, it gets pretty hairy. But it's some good math, and it's very, very important in the grand scheme of our world. All right, so my error propagation rant aside, and the funny thing is I'm not even a huge fan of doing that math, but I love the concept of error propagation. We got our little a being 8.5, so we know this is 8.5. We could put it there if we wanted, but I don't want to. So we know that's the 8.5. We now have 3 sides and an angle. With 3 sides and 1 angle, we can now find another angle. We can either find maybe the angle opposite of C or B, but we said we need to be really careful. We need to make sure that we're not using the largest side because that angle could be bigger than 90 degrees. It's not a guarantee. So that means we can't use the 31 yet in our law of sines. So for law of sines, we have to use what I've called B. We have to use the 24 with the completed A's. So the A over the sine of A would be 8.5 over sine of 10 degrees. I have to use the 24 over the sine of angle B. And I'm going to go to, no, I already did a capital, so I'll stick with capital. Again, you absolutely should not be using the 31 over sine of C because that angle could be incorrect if it happens to be bigger than 90, which we don't know yet. You're going to cross multiply. You'll get 8.5 sine of B equals 24 sine of 10 degrees. You're going to divide both sides by the 8.5. You get used to the pattern of the math, I hope. And you get sine of angle B equals 24 sine of 10 degrees over the 8.5. You're going to take your inverse sine of both sides. And I'm going to skip showing that work this time. The inverse sine and the sine will cancel because we know B is under 90 degrees because it wasn't opposite the largest side. So B is equal to the inverse sine of all that jazz on the right, 24 sine of 10 degrees over 8.5, which when we round to the nearest tenth after jamming in a calculator, let me clear the screen, it's getting a little jumbled. Inverse sine, 24 times the sine of 10 degrees. Now this one you absolutely have to close. Divided by 8.5. It's the trailing ones that I don't technically have to hit this one, but I like to. And we get 29.36 blah, blah, blah. So rounded to the nearest tenth is 29.4 degrees. So that's what we're going to call angle B. We already had side A. So knowing 2 angles, the 10 degrees and the 29.4 degrees, we can find our third angle, which we're calling angle C, capital C. It's 180 minus the others. Which ends up being, so that's 170, 140, then kick back the extra 6, so 140.6. That's our third angle, which is bigger than 90, which means the law of sines would have failed. I'm not going to show that failure this time. Feel free to show it on your own, like I did at the end of A. If you did this law of sines with a 31 here, and the angle C here, it would end up being wrong when you solve for that angle C. I 100% guarantee that. You will get something like 70 or 60 or 50 degrees, somewhere in that ballpark probably. I'm guessing, which is completely way off from what the answer actually is. Last time they were pretty close to each other, and that's because we were just barely in quadrant 2. Now, because we're really trucking in quadrant 2, that means that the calculator would spit out a very, very wrong answer. All right, so we got our 3 components. And remember, you can always put your answer all together in one box. In my math lab, it's going to have the specific spots for everything. So 8.5 is A, then 29, why am I writing the numbers first? B, is 29.4 degrees, and C is 140.6 degrees. Again, on scratch work, I don't care if you're just boxing up as you go or if you put it all together. Either or is fine. I care that your work looks good, you've done everything in the right order, all that stuff. All right, let's do another one. Can I fit it all here? Yes, we can. C. And this time I'm going to label them instead of giving you the triangle. A is 19. C is going to be 4. And then angle beta, let's go back to Greek, will be 61 degrees. Now, it's not as obvious that this is a corner of information. Maybe you need to draw it up. But remember, a corner of information means you have the angle between, and the angle between means you don't have one of these angles. So this is a corner of information. If you drew it up, it would be like 61 degrees is here, this is your 19, and this is your 4. Obviously not to scale. And then your other end is over there. And that's your corner of information, which means we need the law of cosines. You can't start with the law of sines. You absolutely, positively must start with law of cosines. It's the only way to get anything else right now. Now I've labeled these as A, C, and B, which means the formula we're going to need to use is going to have side B by itself. Sorry, I was looking at something else and I was like, that's not right. But we'd use the one with B by itself, the little b. So A squared plus C squared minus not equals, got a little squirrely with my pen there, minus 2AC, then a cosine of angle beta. So we get B squared, and some people will just say, can I just go ahead and write B equals the square root of all of that? Yes, you can. I'm just being methodical. So 19 squared plus 4 squared minus 2 times 19 times 4 times the cosine of 61 degrees. Take the square root and you'll get B equals the square root of all of that. 19 squared plus 4 squared minus 2 times 19. Doesn't look like I have the one in there, does it? Times 4. I'm just going to make that a little better. 2 times 19 times 4 cosine of 61 degrees. And then round to the nearest tenth or whole or whatever my math lab tells you to do. Please pay attention to instructions. Wow, I missed that thing, cut off on me a quarter of a second, if not less, before I hit a button. Square root 19 squared plus 4 squared minus 2 times 19 times 4 times the cosine of 61 degrees. And we get 17.4 when we round to the nearest tenth. That's what we're going to call our length B. Now we do, so that was the law of cosines. Now we do the law of sines. Now, we cannot find the angle opposite the largest side. The largest side is 19, so I cannot find angle A doing this. It could be wrong. And now the first two I designed so they would have been wrong. Maybe this one I will too, maybe not, I don't know. Hint, wink, nudge. But I do love problems that are forcing you to do it the correct way. That way it keeps you on your toes. All right, so I can't use the A's, I gotta go after angle C. So what do we have completed? We have the B's completed. So we're gonna go 17.4 over the sine of 61 degrees, that's the B over sine of B, equals C over sine C, so 4 over sine of capital C, or gamma in this case, since I'm going Greek. Now, once again, rounding this to the nearest tenth, putting it in here, that causes error propagation. This angle will be off by a few tenths of a degree, but no more than a few tenths of a degree. If you don't want to be off, then use the more exact answer here, 17.415766693. But like I said, I think the homework tells you to round in the nearest whole for these because of that, because then it's not really an issue. Cross multiply, you know what it is, 17.4, at least I hope you do at this point, sine of alpha equals 4 times the sine of 61 degrees. Divide both sides by 17.4, giving us the sine of gamma equals 4 sine 61 degrees over 17.4. Take the inverse sine of both sides, ultimately giving us that gamma is equal to the inverse sine of 4 sine of 61 degrees over 17.4. And we know that gamma will be less than 90 because C is not the largest side. Round to the nearest tenth, or whole, or whatever the problem tells you to do. Inverse sine. 4 sine 61 degrees. Close it. Divided by 17.4, or the more exact, if you want a more exact answer, close it. We get 11.59 blah, 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 which will be 11.6. This is an angle, so degrees. That's 61, that's 11.6. I'm willing to bet $1 million that other angle is bigger than 90. How do we find the third angle, which we're going to call alpha? It's 180 minus the others. 180 minus the 61 minus the 11.6. So what's that? 119, 108, so 107.4. That's our alpha. And since that's bigger than 90, we would have had issues with the law of sines. Are we on time? 30 minutes? Oh yeah, we're going to finish this section today, and then we'll call it after that. So that was 3 examples of the side angle side case. 2 sides in an angle. But 2 sides in an angle doesn't tell you whether you're starting off with law of sines or cosines. You've got to know whether they're all tucked in a corner, or if the 2 sides you know are kind of next to each other and then the angle is not the angle between them. Distinct differences there. If I gave you 2 angles, easy case. If I give you 1 angle, it's either the ambiguous case with law of sines, or it's the law of cosines if it's the angle between them instead. But we have not studied the final case, which is when I give you all 3 sides and no angles between them. And you might go, well, hold on, these are all solved for sides. How do you find an angle? Well, there's an angle in each one of these, so you would just take those equations, those formulas, and you solve them for the angle. Now, nobody wants to just blatantly memorize those where it's inverse cosine of a squared minus b squared minus c squared over negative 2bc, and then 2 more variations of that. That sounds awful. Just just plug the numbers into the original formula and do your algebra and solve it that way. And it's algebra that you better know how to solve, better know how to handle that, as I say. So for the side case, last possible case, we're giving you a triangle with 3 components, and you can fill in the rest. And they aren't even a right triangle anymore. So at this point, we've pretty much done all the essential trigonometry we need without going into a more advanced version of trigonometry where we start doing something called vectors. And that'll be the next stuff we do in here. And it's not like it's crazier. It's just, you're thinking about graphs a little differently. Instead of just having points, we're going to have arrows. But let's save that for next time. So it's the side case. We're going to have that, if you end up doing a inverse sine of an angle bigger than 90, your calculator is going to give you a wrong answer. That's still a possibility here. So to avoid that possibility, what we want to do is always find the angle opposite the largest side first. This will avoid doing an inverse sine an angle that could be bigger than 90. That's what that'll do for us. So we'll go ahead and knock the largest angle out first. Then we know the other 2 are going to be less than 90, and we no longer have to keep our ducks in a row. Admittedly, it's not the only way to make sure that doesn't happen. You can attack whatever angle you want, and then in the second step, when you do law of sines, just make sure that you don't attack the largest one. But I just think it's better to do this. Just go ahead and find the largest angle, which is going to be the angle opposite the largest side. Now, with the side case, you're doing law of cosines. You should always find the angle opposite the largest side first. Let me be more specific, by law of cosines. The law of cosines is valid in quadrant 1 and 2. The law of cosines can pick up angles between 90 and 180 degrees. If you go back to the definitions of their bounds, which we've discussed many times, inverse sine is quadrant 1 and 4, inverse cosine quadrant 1 and 2. And I know that seems like such a subtle detail to have to remember, but you have to remember it. So inverse cosine can pick up an angle between 90 and 180. So let's go ahead and get that out of the way. That way, when you go for the second and third, you're not juggling anything anymore. You can do whatever you want. So after you've done that, then use the law of sines to find the second angle, then 180 minus the others to find the third. It's literally the same process. Law of cosines, then law of sines, then supplement. I should say supplement in quotes, because it's two angles, not just one, being subtracted. Some people might say, well, could you use law of cosines to find the second angle? Could you use law of cosines to find the third angle? Yes, actually you could. It is extremely inefficient though, because the law of cosines formula is that big beefy thing, whereas law of sines is much shorter, and using 180 minus the others is ridiculously short. So this, what you see on the screen and what I've said is the most efficient method. It's not the only method, but that's the way I'm going to do things. All right, so example 2, triangle. And for A, we will give you the picture. And I'm going to go 9, 12, and 11 clockwise. Please pretend that that was connected appropriately. Now, I did not say whether these were A, B's, or C's initially, so you get to decide which is A, which is B, which is C. I'm going to now make the decision that I'm going to call the bottom left one angle A, I'm going to call the bottom right one angle B, and the top one angle C. That was my choice. That's a capital C up there. I know it doesn't look too capitalized, but it is. What some people like to do for their capitals is something like that. Give it a little extra dash. And that's perfectly fine. Something I used to do, but I don't anymore. And that's because in my own notes, I don't actually use capital letters. I always use Greek. All right, so I gave you 3 sides. Law of sines requires at least one angle known, so we can't do that. 180 minus the other 2 requires knowing 2 of the others, so we can't do that. But the law of cosines formula has a single angle in each of the formulas based on 2 or 3 other sides. So we could just algebraically solve for this after plugging in some numbers. It's going to be a decent amount of algebra, but it's algebra we know how to do. So I said we should always attack the largest angle, which is opposite the largest side. I have called the 12 the little a, that's the biggest side, which means capital A would be the biggest angle, so that's the one we need to find first. So the formula I need to use is the a squared equals b squared plus c squared minus 2bc cosine of capital A. With this lettering, this is the one I have to do first to make sure I don't mess something up later, to make sure that we go ahead and find the biggest angle now so we don't screw up later. Plug in the numbers and we get a squared, that's the 12, equals b squared, which is the 9, plus the c squared, which is the 11, minus 2 times 9 times 11 times the cosine of angle A, which we don't know. And we got to solve for angle A. All right. Well, this time we are actually going to have to process these numbers because we got some algebra to do. So 12 squared is 144, 9 squared is 81, 11 squared is 121, minus 2 times, let's make this easier. 9 times 11 is going to be 99, and then 2 times 99 is 198. And the cosine of angle A. All right, if we combine what we cannot subtract the 198, that's attached to a cosine. So it's just the 81 and the 121, which will make 202. So that's 144 equals 202 minus 198 cosine of angle A. then we just got to keep doing our algebra. So we're going to subtract 202 on both sides, which will give us 144 minus 202. What's that? Negative 58. And then that's negative 198 cosine of angle A. We're going to divide both sides by the negative 198. It's a lot more algebraically intense than before, I know, but the negatives will cancel. Let me just go over here for space conservation. I'm not going to worry about reducing that fraction because we know it's going in a calculator. 58 over 198 equals cosine of angle A. And then we take the inverse cosine of both sides to cancel out that cosine. So we get inverse cosine of the 58 over 198, and then inverse cosine of the cosine of A. The inverse cosine and the cosine will cancel as long as we're in quadrant 1 or 2, which we definitely are. All triangles have angles between 0 and 180, so it would be impossible otherwise. So that says the inverse cosine of 58 over 198 should be angle A, which will round to the nearest tenth. Inverse cosine 58 divided by 198. Drum roll. 72.96, which the 0.96 when we round up would become 0.10 in one single digit. So we end up rounding to the nearest whole anyway. So it's 73 degrees. There's our angle A. That is the largest angle, which for this particular problem, what that means is we couldn't have screwed anything up. We could have done them in any order. But again, we don't know that to begin the problem. No one does. You might do 1,000 of these and have an inclination. But even after that many, you're not going to know. I will be 100% honest with you. I don't know when I start these problems unless I already have done them, whether it would be a problem or not. I have a way of creating them to make sure one of them is bigger than 90. I can do these problems backwards and reverse engineer them is the way I do it. But I can't just make up numbers on the fly and guarantee it's going to work unless I make 2 of the 3 just absolutely ridiculous. All right, so now we have angle A. There's 2 angles left. The next step is always law of sines to make it easy. Yes, we can certainly do law of cosines to find all 3 of these. And if you did that, you would guarantee that you never have to worry about any of those angles being incorrect because you're never doing an inverse sine. But you saw how much math we just did to get that angle. Do you want to do that 2 more times, or would you rather do law of sines and then 180 minus? Yeah, I'm going to do that. So the second step, we put down here, that's the law of sines. And it doesn't matter which one we pick. So the completed one is the A's, so we got 12 over the sine of 73 degrees. And let's go after the B's. I'll go after the smallest one because, like I said, it doesn't even matter. 9 over sine of B. You're going to cross multiply, and you'll get 12 sine of B equals 9 sine of 73 degrees. You're going to divide by the 12. I'm going to stop writing all the little details because this is the 50th time we've done it now. So we get that the sine of angle B is 9 sine of 73 degrees over 12. Yes, you can reduce the 9 and 12, but nobody cares. Take the inverse sine of both sides, and you'll get B equals inverse sine of 9 times the sine of 73 degrees over 12. Rounding to the nearest tenth. Second, sine. 9 sine 73, close it, divided by 12, close it. And we get 45.8 blah, 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 rounding to the nearest tenth, so just 45.8. That's an angle, so degrees. You could use law of sines to find the third one. You could use law of cosines to find the third one. Both of those are going to be way longer than just doing angle C is 180 minus the others. That's that 107, 67, 62, 61.2. Yes, I do my subtraction from left to right. I'm a freak. Don't be mad about it. I don't know what it is, but it's easier for me to subtract in my head from left to right than right to left. You don't have you just have to kind of predict the borrowing. And it might sound weird, but if you do it a million times, it's easy. So that's our angle C. And there we go. We were given 3 sides. We found 3 angles, and they're going to be pretty accurate. So this is the first problem I've given you so far that you couldn't have screwed up by not attacking the largest angle first. But again, we didn't know that to begin with. We had no way of knowing that to begin with. All right, with our last 15 minutes, let's rock this last one. I thought we'd get to finish early, but yeah, not so much. That's okay. We got class time, we're going to use it. Give you another image. Let's go 10, 15, 18. And by my choice, I'm going to call angle A the 18. If you're given the choice, maybe you just always make A the largest one, and that would be a helpful reminder to just always attack the A's. I'm going to call B this one and C this one, or maybe you just always go A, B, C in that order. I don't know, I don't care. If you're not told what letters they are, make your choice, make it good. So we must attack angle A first because that's opposite the largest side. We have no other choice because things could go wrong otherwise by the end. This angle will be right, but others might be wrong. All right, so going after angle A, that means I need the one that says A squared equals blah, blah, blah. So that'll be 18 squared equals 10 squared plus 15 squared minus 2 times 10 times 15 times the cosine of angle A. What's 18 squared? I don't feel like doing that in my head. That's 324. 10 squared is 100. And then 15 squared, that's 225, right? Yeah, 225 plus 225. And minus, that's 20. 20 times 15 is going to be 300. Cosine of angle A. The 100 and the 225 are going to make 325. Subtract 325 on both sides. Remember, you can't subtract the 300 because it's got the cosine term. So we get -1 equals -300 cosine of angle A. Divide both sides by -300. Up here, so that gives us 1/300 is equal to the cosine of angle A. Take your inverse cosine of both sides. So the inverse cosine of 1/300 would be your angle A. Now that's 100% accurate, but you know that we want to approximate that to the nearest tenth. So second cosine, 1 divided by 300. Close it, drum roll. We get something really, really, really close to would have caused a problem later, but that largest angle is 89.8. So again, for this one, we would have been lucky, and any order we did, it wouldn't matter, but we didn't know that to begin with, so trust me, do this one first. So that says 89.8 degrees is about angle A. We got our first one. So that was our law of cosines. Now we go to law of sines. Let me just put that on the next page. Law of sines, doesn't matter which one we grab since we already have the biggest angle. We know the others have to be less than 90 degrees for very obvious reasons. So what do we have completed? We have the A's completed, which is 18 over the sine of our 89.8 degrees. And then we can go after the B's or the C's. It doesn't matter, I'm gonna go after B's because alphabetical order. So 10 over the sine of B. You're gonna cross multiply and you'll get 18 sine of B equals 10 times the sine of 89.8 degrees. You're gonna divide by the 18. So we get sine of B equals 10 sine of 89.8 degrees divided by the 18. Then you take your inverse sine and you get angle B equals inverse sine of 10 times the sine of your 89.8 degrees. We're almost there, all over your 18. That's an ugly 8. Let's try that one more time. There we go. Nobody said my handwriting was pretty. So inverse sine times the 10 times the regular sine of 89.8. Just imagine if you get one of those signs or inverse signs backwards, everything's wrong. Divided by the 18. And we get 33.7 when we're round to the nearest tenth degrees. So that's our angle B, which means our third angle, which we called C, is 180 minus the others. What's that gonna be? 90.2, 60, 56.3. No, 56.5. 0.2 minus 0.7, 56.5 degrees. I don't know why I said that first one. So that would be our C rounded to the nearest tenth. A, B, C, and we got them. We're good.
I just wanted to leave that up there for another like 20 seconds because I'm sure some of you are still writing. But anyways, that concludes 7.2. So we have finished 7.1 and 7.2 today as promised, just in the nick of time. But again, I know that our priority for the next day or two is going to be studying for the test and taking the test. So again, hopefully you know the expectations. If anything is unclear, please email me and I'll gladly answer any of your questions. But besides that, best of luck to you on the test. Email me letting me know what kind of partial credit you think you need, and then get to work on that chapter 7 stuff immediately because we're going to keep pushing and pushing and pushing. We got 3 weeks left and we're going to finish all the material we have to. We'll have just enough time. All right, good luck. Take care. Have a good weekend.